Today we're going to look into different topics like the shape of the Earth, and also we'll start to get into the latitude and longitude system and understand a little bit more about that. So first though, I want to explain a little bit about something that you're going to hear me talk about in the really upcoming weeks, and that is going to be the four spheres of physical geography. So the four spheres of physical geography are those categories, if you will, of different topics that we'll cover. So let's think about this. So one thing that's kind of interesting is that really from looking at the Earth from outer space, such as with this image here, this is something where we can actually see the four spheres of physical geography all with the naked eye, really, without having to use any special binoculars or anything from outer space, or any type of telescope or anything like that. So let's think about this. We have, with the four spheres of physical geography, there's going to be the atmosphere, all right, and you can see that definitely, with the clouds there. Then there's also the hydrosphere, which deals with water, right? So you can see that with the oceans. Then there's the lithosphere. Lithos being Greek for rock. So in this case, we're looking at, we can see some rocks, really some terrain, right? Some land. As we see, the continent of Africa over there and the Middle East, just north of it, northeast of it, really. What we end up finding, though, is that, okay, so we can see those three spheres there, all right? And indeed, really, the first half of the semester, we're going to be dealing with the atmosphere for the most part. Then we go to the lithosphere, then to the hydrosphere, and really from time to time, we end up covering this fourth sphere, the biosphere. So all living things, plants, animals, humans, and so on. So in this case, we can actually see the biosphere without any type of special technology or equipment. When you look at it, try to see if you can find out where the biosphere is based on this image. And I'll give you a few seconds to do that before I move on with it. But kind of keep in mind is something related to maybe plants or animals or people. Right? When you look at it, let's see. So not so much in the Sahara Desert that we can see north of the northern parts of the African continent, or in the Middle East and so on, or Somalia over here. But actually, if you look at the center of the African continent, this is where we see a lot of different forests, rainforests and other forests, savanna forests, those type of things. And so that is really the kind of the green that you can see from outer space, really, whenever you go over any type of really forested areas. So with that said, then we're going to cover those four spheres. So the atmosphere for the first half of the semester, and then the lithosphere and the hydrosphere, and from time to time talking about the biosphere as we go along. Well, I talked about how different geographers asked all these different questions about the planet and so on. Well, let's have a look at this question here. Is the Earth round? Well, I mean, we have all this evidence now that we can see from, just for example, astronauts going into outer space, and we can see, the curvature of the Earth, and we can actually now watch videos on YouTube of the International Space Station, flying overhead live, and so we can see that okay, so the Earth does have a round shape. So that is part of the evidence that we have nowadays. We have this convenience of having all these different satellites and astronauts and so on. Going up there and showing us that okay, so the Earth is this round shaped figure moving through the cosmos. Well, the other question may be, is the Earth a perfect sphere, though? So we're going to get to that in just a little bit. But I also wanted to mention that even in ancient times, during the times of the ancient Greeks, remember we talked about the ancient Greeks and how they were trading around the Mississippi, not this is where I'm from, the Mediterranean, not the Mississippi. So the Mediterranean. So they have all these different sailboats, and as people would go off into the distance on these sailboats, if the Earth were flat, people would see those sailboats as they ended up going across the horizon. They would see the entire sailboat itself shrinking. So they would always see the entire sailboat as much as they could over the water, right? They would see that shrinking until it became a little dot. But they didn't see that. They saw that as the sailboat moves off into the horizon, as it gets close to the horizon, it looks like it's sinking. So at a certain point, then all you see is the sail itself, right, until it shrinks into a little dot. And then, well, that kind of led a lot of people to figure that the Earth can't be flat if that's happening, because those sailboats, they were coming back and they weren't reporting being sunk or anything. So, you know, that says that, well, there's something going on with the shape of the Earth there. So indeed, that's how, you know, even in ancient times, a lot of people understood that the Earth is probably not flat, even though a lot of people believe so as well at the same time. Now, the thing is, though, that indeed the Earth is round, but it's not a perfect sphere. We can see that nowadays with, for example, laser measurements from satellites and so on. And we end up finding that, you know, when you look at the dimensions of the Earth itself, they find that if you were to take an imaginary line, really from pole to pole, okay, and then if you were to take the other major imaginary line that we all know of, the equator, and you were to compare those two, you were to compare the diameter of both, we find that the poles, that line that goes from pole to pole, that diameter is going to be smaller, albeit not very much so, but smaller, but it is going to be smaller than the diameter of the equator. So when you look at the numbers, okay, yeah, indeed, it's not really by that much as far as a difference, but we find that, and you don't have to memorize these numbers here, but it is interesting for reference. The number 7,900 miles diameter from pole to pole versus 7,926 miles in diameter from around, you know, just going around the equator. Well, okay, so there's a difference of 26 miles, so there's a little bit of a distortion there. So it's saying that the Earth is a little bit flatter on the tops and bottoms and a little bit wider around the middle. So with that said, we're going to get into a little bit later about what exactly is the Earth as far as its shape. But a couple major terms that, you know, I'm going to be referring to from time to time. It's good also to jot down. Indeed, the poles themselves. What I'm going to be talking about pretty much for the next several chapters, when I'm talking about the poles, it's going to be the actual North Pole and South Pole that's in a fixed position. It's in one single location, doesn't move around. That's in contrast to the magnetic poles, the magnetic North and South poles, which end up basically moving around the surface of the Earth from place to place from time to time. So we'll come back around to talking about that in the middle of the semester when we talk about topics related to that. But for now, and for the next while, we'll be talking about referring to the poles as the actual North and South Pole in one location. So if you were to, you know, draw an imaginary line from one pole through the Earth to the next, that would be the axis of rotation, okay, around which the Earth rotates. So in this case, though, when we think about the North Pole and South Pole, and you think about you know, how they're aligned, well, they're not aligned to where the North Pole is exactly on top of the Earth and the South Pole is exactly on the bottom. Instead, the Earth, as we'll see, you know, in various times in the next couple chapters, the Earth is tilted on its axis, as we say. So there's no completely, you know, vertical up and down axis, right, that the Earth has. Instead, the Earth is tilted at 23.5 degrees. And I'm being very specific about that number because that number is going to become very important in Chapter 2 when we talk about the seasons. So it's going to help us understand a little bit more about why we have seasons, first of all. So indeed, the Earth is tilted on its axis at 23.5 degrees. So with that said, though, okay, so let's get back to talking about the shape of the Earth, right? With that said, let's have a look at this idea here. Well, somebody had the idea that the Earth was not a perfect sphere even before having the advantage and the luxury, if you will, of having satellites with all their laser measurements and so on. So somebody who first hypothesized, the first kind of question, is the Earth a perfect sphere or not? And he kind of had this idea that perhaps it's not. Well, who could that be? Well, it was actually the same person who, say, for example, had some other impressive feats going on. For example, inventing calculus at the age of 26, and developing all sorts of laws and so on related to gravity and physics and so on. So, in the 1600s, that's when he did all this. So, if you guessed Isaac Newton, that's correct. Indeed, Isaac Newton was the one who first realized that, you know what, the Earth may not be a perfect sphere after all, even if, you know, he's convinced that it's round. He was able to at least hypothesize. There really wasn't anything that he could use for specific measurements to give him exact evidence once and for all. But once we started to, you know, have all these satellites, then yeah, it made it really confirmed his ideas. So what happened there was that Isaac Newton figured, well, okay, so the Earth then, you know, he calculated that the Earth, at least at some parts, is moving at over 1,000 miles an hour. So we're really, you know, the Earth is spinning on its axis. It's rotating on its axis, right, to give us our 24 hours of day and night. It's spinning on its axis at, in some parts, over 1,000 miles an hour. So we don't really experience it as far as we don't really experience feeling like we're going 1,000 miles an hour in circles, but in fact we are. I mean, we can kind of see, you know, when we look at the night sky and we can see the stars moving across the horizon and you know, just across the sky really, and then also the sun itself moving across. I mean, we kind of experience it that way, but it looks kind of slow. But what, you know, Newton had realized was that, okay, if you have any type of object that's spinning very fast, well, naturally, if it's spinning fast enough, it's going to actually become a little bit flattened on the tops and bottoms and wider around the middle. So if you spun, say, a top fast enough, and it would have the correct material that you can actually see this, you would see the top actually being shortened a little bit on the top and bottom and widened in the middle. Especially with some type of a globular type of top there. So with that, you know, he came up with that idea, and it wasn't until later when we could really confirm it. Nonetheless, you know, from this and other studies, we ended up coming up with a entire field of study called geodesy, which is studying the shape of the Earth itself. Now, this field, since, you know, the Earth's shape is not really all that much disputed anymore, and even around some of the details, but nonetheless, there are some things that researchers are looking at here and there. But this is kind of a very small field nowadays, and, you know, you have a few maybe geologists and maybe a few physicists, a few geographers also getting involved in this field of geodesy, studying the Earth's shape. But as far as then figuring, well, okay, answering the question, is the Earth round, right? Yes, but is it a perfect sphere? No. So what type of shape is it? Well, very commonly in textbooks and so on, they refer, even, you know, within science too, and you'll hear scientists talk about oblate spheroids. And an oblate spheroid then, okay, well, first of all, oblate means anything that is kind of a little bit flatter around the tops and bottoms and wider around the middle. Okay, that's an object that's oblate. But then spheroid, spheroid kind of implies that that shape is a perfect sphere. So, and it's something that's oblate and yet a perfect sphere. It's kind of a contradictory term in some ways. So, in fact, while that's okay to call it an oblate spheroid as far as referring to the Earth, what is more accurate, you know, more technically accurate, is that the Earth, then, being oblate, it has a little bit more of an ellipse shape. So it's actually most accurately considered an oblate ellipsoid. Okay? So it's an oblate ellipsoid most accurately, even though, you know, if you can refer to it as an oblate spheroid, that's fine. It's better than referring to it as like a perfect sphere or something like that. All right. Well, what does all this have to do then with, you know, anything else as far as maybe things that relate to our lives? Well, we need to be able to locate ourselves, right, wherever we are. Say, you know, using a GPS system in your car, we need to be able to, given that we have an Earth that's the shape of an oblate ellipsoid, we need to be able to locate ourselves on the planet. Now, because the Earth is, generally it's a round shape, this creates a lot of problems when it comes to drawing maps, and in terms of flat maps, not necessarily globes, but flat maps. And also then it makes it difficult for us to be able to locate ourselves precisely, okay? Because let's think about this for a little bit. So we have then, in this case, let's have a look at the illustration. So let's say you take a globe, and you can really do this with any type of round object, soccer ball, basketball, whatever. You can do this with any round object, but here we're looking at a globe, and we're putting a piece of paper around the globe with the intent of tracing the shapes on the globe, right, the different continents. Okay. Well, if you do that, if you try to cover that round object with the flat sheet of paper, and then you trace the objects, well, when you go back to flatten that paper again, something gets distorted. It could be the shape of those continents. It could be the distance of one place to the next. It could be the area of some of those continents, and on and on. So, there are multiple issues and basically multiple types of distortions that happen whenever you try to, as we say, we kind of create a map that's flat from a round object. It doesn't quite work. Now, anytime that you try to attempt to create a map, a flat map, okay, anytime you try to create a flat map from a round object, this is what's called a map projection. So you're projecting the round objects, the details from a round object onto a flat screen or onto a flat piece of paper, right? And indeed, the idea is that you kind of hope to be able to accurately reflect what is shown on the globe. However, there's always something that's going to get distorted. So, as it says here in the second line there, curved surfaces cannot be projected onto a flat sheet, right, or a flat screen without some type of distortion, one way or another, area, shape, size, etc. Now, with that said, here we have on the right-hand side, we see one of these types of projections. There are many different types of projections that cartographers have developed, each one trying to maybe distort as little as possible the world map. However, a lot of times there are just a lot of trade-offs. Sometimes in order to get a very accurate shape of the continents, you have to distort perhaps their size, or you have to distort their distance, and then vice versa. If you're trying to create the accurate distances from one place to the next, well, you're going to have to distort sometimes the shape, etc. And so here we see one of the most common types of, on the far hand right side of the screen, we see one of the most common types of projections, and this is called a Mercator projection. Okay? And you'll see a video clip that I have that talks about some of the problems with this Mercator projection. Now, just very briefly, before we look into it, we can look into, the idea that probably for many of us, the maps that we would always see, in classrooms in school, right? Those maps, a lot of times, were Mercator projections. How do we know? Well, it's the ones that have, for example, Greenland over here being much larger than it really is. You can fit 9 Greenlands inside South America. However, in real life, however, the map expands Greenland so much that it looks impossible to do so. But you can fit 9 Greenlands in South America. So the idea is that, as we'll see here, pretty much places around Canada, Greenland, Alaska, Russia, and then on the south, in the southern hemisphere here, we end up with Antarctica. Those end up becoming a lot larger than they really are. And then around the equator, okay, we see Africa, South America, and so on, these islands here, for example, Indonesia, becoming a lot smaller. So that's the distortion that we're talking about, that we see there. So I won't talk about it too much anymore as far as this goes, because I'll let you watch the video clip. However, the video clip talks about which projection is it that they're really trying to use a lot more nowadays in classrooms, etc. Well, it's the Winkle triple projection, and that one is one that they basically try to compromise on everything that can be distorted. They try to distort it just a little bit, but so it looks about as accurate as you can get as far as everything. However, keep in mind that the projection that they're looking at as being more common nowadays, and they're trying to use it more than these Mercator projections. That's going to be something that it still distorts the planet somewhat. So it's not there are no 100% perfect projections. Okay. Now I also have up here a system of parallels and meridians. Well, the thing is that because of these issues with especially distortions and so on, we need some way to be able to locate ourselves on the planet no matter which projection we're using. Okay. So we use what's called a system of parallels and meridians, otherwise known as the geographic grid. More commonly, we refer to these as latitude and longitude. Okay, so latitude and longitude, that's the geographic grid. It's a network of parallels and meridians. Parallels and meridians being the vertical lines or horizontal lines, as we'll see. The parallels are going to be the horizontal lines. Okay, so let's actually, since we're looking at here, the census up on top, network of parallels and meridians. Let's just look at, so let's go with parallels down here at the bottom. Parallels then, they're east-west circles on the Earth's surface. So basically they're the horizontal circles that we see here. Okay, and they lie on a plane parallel to the equator. So here we have the equator. Every other line is parallel to the equator, okay, and really to each other. But in that case then, that's going to be latitude. Okay, so parallels, that's going to be latitude. Meridians, on the other hand, right, those are going to be the north-south lines that we see, and they're going to go basically from pole to pole. Okay, so with that said, you're gonna find that the confusing part about this is going to be where even though the meridians run north and south, we actually refer to our location regarding meridians or longitude east and west. Opposite for parallels or latitude. Even though those lines go east to west, we locate ourselves in terms of how far north or south of the equator we are. So the equator is kind of like the reference line. The meridians, for the meridians on the other hand, the longitude, those are going to be where we have the prime meridian as the reference line. And so we're going to look at a lot more visuals on this, but the thing is we locate ourselves regarding meridians based on how far we are east or west of the prime meridian, which runs through England and West Africa. All right, so I just gave you a lot of information here. I think instead let's go ahead and, just to give you a brief preview into that, let's go ahead and look into this a little bit more. Again, as I mentioned, there are going to be several slides that we look into with this geographic grid, so we all kind of get it. It's basically one of these things that will take some time, will take some practice. Sometimes we'll take thinking through this a few different times at least in order to finally get it kind of established. So I encourage you to practice this, think about this, after the lecture, just as you would, in a regular classroom. Where you're getting all this information, and it is going to be a lot of information at first, and maybe within a short amount of time. But let's have a look then. So the equator, it's on the left here. The equator is a parallel of latitude, right? So it's one of the parallels. That's midway between the Earth's poles. Now it gets designated as 0 degrees latitude. Okay. So what ends up taking place with latitude, and so it's going to be different from longitude, but with latitude then, you go from 0 degrees at the equator to 90 degrees at the poles, each pole. Okay, so you have 90 degrees, we say north for the North Pole, and then 90 degrees south for the South Pole. Why 90? Well, the Earth itself is 360 degrees. So when you go from the equator at one spot to the North Pole, let's say, that's actually 1/4 of the way around the planet. Okay, that's why it's going to be 90 degrees north. Okay. Meanwhile, we see that overall, the reason why we call it a geographic grid, right, is because when you put the two together in meridians and parallels, right, it ends up making a grid pattern there. So speaking of, looking at going from 0 to 90 degrees, right? Around Michigan and Oregon, those areas, we end up with places that are somewhere, along the 45th parallel, which means that they're at 45 degrees north latitude because they're between the equator and the North Pole. Okay. So they're 45 degrees north latitude. And I'll stop pretty soon with this video, and then afterwards we'll look into a video that starts us off on longitude. But for now, yeah, indeed, with latitude, then we see these are parallels. Another way to think about it is your location where you are, right? Based on latitude, we are going to be basically, one way to think about it is that you're at a certain distance from the equator, of course in miles or kilometers, but you're also at a certain distance from the equator based on degrees from the equator. So in this case, where P is, right, that looks like that's like getting almost to 45 degrees, right? We're looking at 10, 20, 30, 40 degrees latitude. That's where this P is. So it's 40 degrees away from the equator. That's what it's saying here with angular distance. It's 40 degrees away. So we're not really talking about miles or anything like that when it comes to latitude and longitude. Another way to look at it is you kind of saw how I was looking at these different steps, if you will, these different horizontal lines, right? Every horizontal line here is 10 degrees of latitude. So in this case, then you have the equator, 0 degrees, 10, 20, 30, and then 40 where P is. Okay, that is kind of like steps of a ladder, really. So if that helps you to kind of remember which is which, I always encourage you to kind of think of whatever you can, or use whatever you can as far as anything to help us remember, what's latitude, what's longitude, no matter how cheesy it is. So if you want to think of it as steps of a ladder there, then that should work. But yeah, that's the idea then. So you have the equator itself dividing, when I'm talking about the northern hemisphere, right, everything from 0 to 90 degrees north, and then the southern hemisphere 0 to 90 degrees south, all the way around the planet. Now, something that you're going to hear me refer to really in many different chapters throughout the semester are what are called the low latitudes, the mid latitudes, and the high latitudes. And these are just different zones that scientists have named, and basically different zones of latitude from 0 to 90 degrees, okay, north or south, all right? And we see a lot of them here. If you look on the right, you can see all these here. And what we'll do then is there's another slide that I'll use to help us kind of jot this down and remember this a little better. But you see, for example, one of these zones. Well, this is there's several zones that we see from the equators and poles. However, when it comes to the low and then the mid and then the high latitudes, okay. The low latitudes are going to be, so each one of those low, mid, and high, each one's going to be a third of the way up towards the pole. But 0 to 30 degrees then, so the equator up to 30 degrees, those are going to be the low latitudes. 30 to 60 degrees, those are going to be the mid latitudes. And 60 to 90 degrees, those are going to be your high latitudes. All right. So with that said, we see that those latitudinal zones are subdivided into even more zones here. So the next slide will help us kind of with that. But indeed, that's what we end up seeing, is that we go 0 to 30 for low latitudes, 30 to 60 for the for mid latitudes, and then 60 to 90 for the high latitudes. So yeah, with this list here, I like to actually go from the bottom to the top here. So let's have a look then around the equator, right, at 0 degrees. Okay. What we end up seeing is a zone, a latitudinal zone, that's going to be going from 0 to 23.5 degrees. So there's that number 23.5 degree again. So again, we'll refer to that back to that in the second chapter. But there's that zone there that's called either the equatorial latitudinal zone or the tropical zone. Okay, either way, equatorial zone, tropical zone, or equatorial latitudinal zone, tropical latitudinal zone. Now, as we'll see later on, the next one is going. Let's say we're going from the equator to the North Pole. Well, going a little bit farther north, we're going to end up in the subtropical areas. Okay, and then if you go a little farther north, the mid-latitude areas. Now, what I would like you to know as far as the exact numbers, let's go with 0 to 23.5 for the equatorial ones, okay? But then later, let's go with we'll see 66.5 to the pole. I'd like us to know, those exact numbers for the equatorial areas and the Arctic or Antarctic areas, and then everything else is kind of in between there. But what we see though is that we basically go farther north, you go to subtropical zone, even more so you go to the mid-latitude. Then when you get farther north, okay, well now you have two different options. There's going to be the subarctic or subantarctic. Well, in the northern hemisphere, think of the Arctic Ocean. The Arctic Ocean is in the northern hemisphere. So in the northern hemisphere, this latitudinal zone is called the subarctic zone. And then if you just go farther north, really up until almost until you get to the pole, you end up with the Arctic zone. So from 0 degrees to 90 degrees, we see that the numbers themselves end up getting larger and larger, right? Really, they end up going higher and higher. So if you're wondering about, okay, well, what is a higher latitudinal zone, like 80 versus, say, 20? Well, just think of the number. Well, which number is higher, right? So the higher the number, of course, 80 is going to be a lot higher than 20. So the higher the number, the higher you are in the latitudes. Okay. So when you look at it then, if we were to the opposites, really you'd have the same three zones. Okay, if you were going to go from the equator to the South Pole, if you were going to do that, we would see that you would have these three same zone with the same zone name. So equatorial or tropical, it doesn't matter. You can call it either way. It doesn't matter about the hemisphere. The only thing that changes with the hemisphere then, subantarctic in the southern hemisphere and Antarctic zone in the southern hemisphere as well. Otherwise, then these bottom three zones, they don't change the name whether you're in the northern hemisphere or southern hemisphere. So equatorial tropical is just that's just depends on what you want to call it. Okay, yourself. So, all right, and then to end our talk for now, last thing I want to talk about with latitude has to do with something that seems kind of strange and it seems like it's not really related to anything, but in fact it becomes incredibly important for people who are navigating many thousands of miles, or even sometimes many hundreds of miles too. So let's think about this. Let's look at this scenario. If you were to put the Earth, maybe a globe, right, on a chopping block, okay, and you were to start to slice the globe itself. Now, as you go from different areas, you start slicing more and more. So, we find that there's only one place where, if you were slicing that Earth in half along the latitudinal lines, okay, then you have two equal halves. Okay, so two halves of equal size. So that would only be the equator. Okay, everywhere else, all the other latitudinal zones, if you were to slice the Earth along those latitudinal zones, you would get one side of the Earth being larger than the other. Well, let's see what this has to do with anything, because indeed it does sound kind of strange. So yeah, let's have a look here. So you have, all right, so you have the equatorial parallel, right, is the great circle. Okay, so you have the equator being a great circle. And then when it's sticking with the parallels, all the other parallels and all the other lines of latitude are going to be small circles. Just a little quick heads up, on the left here we see that each pair of meridians, so each line of longitude is a great circle, but those are the vertical ones. So we'll come back to that in the next video. Meanwhile, if you look on the right, then you can see the great circle is basically anywhere. It doesn't have to be just the equator, but it's basically anywhere that splits the Earth in two equal halves, unlike at the bottom here, the small circles. It does not. Well, let's think about this. Okay, so how does this end up being useful? The thing is that we all grow up a lot of times learning that the quickest route from point A to point B is a straight line. We hear that so much. And that's true until you start to travel at least hundreds of miles. Then you end up with a different situation. And this all has to do with the fact that the Earth is a globe, and that it's not flat. Let's think about this. So if you were to take a flight then from, say here we have San Francisco to London, right? If you take the conventional wisdom that the quickest route from point A to point B is a straight line, you would be flying along what's called the rum line. Okay, the rum line is basically it's just not a line that gets us where we need to go efficiently, but it's a line that looks like it does, right? But meanwhile, what pilots have to do in this case, and what really a lot of times sailors, when they're traveling across the globe too, they have to calculate where is the Great Circle. The Great Circle, okay, that's going to be just someplace where, if you were to again split the Earth in two along that Great Circle, you would end up with two equal halves. But more importantly, right, you would end up with, more practically in this case, more practically, you would end up with your most efficient route, your quickest route. So if any of you have flown, let's say, from New York or Chicago or even Houston or anywhere else around the U.S. to Europe, chances are, if you saw a map of where you're flying, chances are you saw that you were flying over much of middle or northern Canada and then over off to Greenland, maybe around Iceland. And so, in case you're curious about why they were doing that, I mean, it wasn't any type of detour or anything like that, but they were flying along the Great Circle. Now, what I'd like to do is to show you, you can do this on Google Maps to some extent, and it's actually, much better with a globe, doing this on a globe, an actual globe, than on a flat map. But nonetheless, we can still kind of approximate it. So let's have a look here at, alright, if you right click on Google Maps and you go to measure distance, and then you click, let's go to San Francisco over here. Oops, looks like I clicked out there in the Pacific. Okay, if you go to San Francisco over there, but then you go over to London, right? Now notice what Google Maps is doing automatically. They're making as much as they can for a flat map. They're making the routes of the Great Circle, and notice it's just like what we looked at here, right? With this Great Circle as well. So that's something that you just want to kind of keep in mind for those who are traveling, thousands of miles at least, or maybe even at least hundreds of miles. This is what ends up taking place. All right, now here's a change of perspective, because now we have a straight line being the Great Circle. Okay, so what's happening here? This is something that you may run across in review questions. So let's think about this. Well, this is just a view from a different perspective. This is a view from up top, and we end up seeing that the Great Circle looks like a straight line nowadays, and the rum line looks like a curved line. So you have to be sure you're correct on the perspective, that indeed you are in fact calculating the Great Circle and not the rum line. So that's the idea with that.